Hello, am I audible and visible? Alright, I'll get started with today's session. So, good afternoon for those of you who have joined. I am Shreya Chakraborty and I will be the TA, one of the TAs for this course on regression analysis. So, these sessions will primarily focus on doubt clearance and problem solving. So, I would urge you to interact as much as possible. If anywhere you face problems, just unmute yourself and ask questions. There's no issue in that, and get your doubts clarified. Okay, so there will be, this is typically a 12-week course. Every week the materials would be released on the website. You would have to go through them and then you are expected to answer assignments. So what we are going to do is that we are going to help you solve those assignments by solving similar problems or clarifying concepts. Alright, but we won't be solving the exact assignment questions before the deadline is over. After the end of the deadlines, then if you have any questions, you can raise those questions and you can ask us. We are going to solve it, but we cannot solve the assignment questions that you are expected to solve before your deadlines. All right, so I can see only one person has joined, so I would request you to unmute yourself and just tell me what your background is, so that it is a little easier for me to make you understand. First of all, just let me know if I am audible and if the screen is visible to you or not. Shuma Ghosh, am I audible to you?
Yes.
Okay. And is the screen visible?
Yes, it is.
Okay. Okay, can you please tell me a little about yourself, like what your background is?
Currently, I am an assistant professor in engineering college,
Okay.
and I have PhD and have some postdoctoral experience.
Okay.
Yes.
All right.
So, and I have some idea on regression model.
Okay.
We need
So,
also in machine learning.
okay. So, what are your expectations for this course, ma'am?
Some nonlinear regression.
Okay, but this course is focused on linear regression
Okay.
and not
Okay. No,
non-linear
no problem at
regression.
all.
Okay, ma'am. Fine.
Okay.
So, alright, then I'll just get started on this course. And for everyone else, these sessions will also be recorded, and the recordings and slides will be made available to you. And if you still have questions, you can post those in the Google group, the discussion forum, and one of the TAs are going to answer to that. Okay, somebody from the team is going to answer to that. So I'll just start with the course. Okay, so the first thing that we should keep in mind is why do we study regression and what do we exactly mean by it. Okay, so regression analysis, there are basically two purposes. One is to so what do we mean? First question is, what do we mean by regression? Now we have two sets of variables. Let's say one is your independent variable and one is your dependent variable. Okay, we want to check what impact or effect the independent factors have on the dependent variable. For example, if we take the dependent variable as yield of a crop, this can depend on several factors. It can depend on rainfall, it can depend on the fertilizers, it can depend on the soil quality. Okay, so these aspects are actually my independent variable, and the yield of a crop actually depends on these factors. So this is my dependent variable, also known as the response variable, and the independent variables are also known as predictors. Okay, in a typical setup, the response is designated by the variable y and predictors are designated by variable x. Okay, so this is one example of one case where regression can be used. Okay, another case is that, let's say, this is case one. Let's say revenue in a company. Okay, it can depend on several factors. It can depend on investment, it can depend on the ads and advertising, those kind of factors. It can also depend on something else. Okay, so other factors. So in this scenario as well, the revenue of that the company generates is going to be the response variable, and these would be our predictors. Okay, so what do we want to find out? By a linear regression, we want to find out a linear relationship that would tell us something about the magnitude of the effect and also about the direction of effect. Okay, is it affecting positively, is it affecting negatively? Okay, and also one more purpose of this thing is to main goal is to forecast or predict. Alright, let's say I have a data set where I have 10 data points and I have data on X and Y. So what I'm going to do is that with this data set, I'm going to fit a linear model and then use this model to, I'm going to get some equation y equal to some function of x plus some error term. Because exact modeling is not possible, I'm going to only draw a sample and then base my estimates on that sample. So this would be my model which I'm going to fit, and then I'm going to get some prediction, which is y hat. So then if I can predict some parameters of this functional form, then given an unknown x, I will be able to predict or forecast what my value of y should be. Okay. So for this week, what we have done is that we have studied simple linear regression. So simple linear regression. Here what we have studied is that we have one predictor, one response, okay, and we have only one predictor, which is x, and we are trying to find out how x is affecting y, what is its magnitude by which it is affecting, and what is the direction. Alright, so this is what we are going to study today primarily. Now, given a set of coordinates, let's say x and y, where x is also a continuous variable, it could be discrete as well, but let us stick to the continuous cases, and y is also a continuous variable. What I mean by continuous or discrete is that x can take any range of value in the real line and y can also take any range of value in the real line. Okay, so when x and y are both continuous variables, then the best way to visualize is by a scatter plot. Alright, so how do we plot a scatter plot? We take two axes. This is the x axis where we plot our x, and this is the y axis where we plot our y. Now for every point, specify the coordinate in this 2D plane. Okay, so we have a set of n xy coordinates and we plot it. So then we are going to land up with something like this. Let's say, now intuitively we can see that as x is increasing, y is also increasing. So there seems to be a positive impact of x on y. Okay, so then what regression is going to do is that we are going to fit a line which we'll call as our regression line in such a way that this relationship, okay, the strength of linear association is captured by this line in such a way that the error part that I was talking about is reduced. Alright, so the general model is y equal to fx plus epsilon. In case of a simple linear regression, what we do, fx is actually beta naught plus beta 1x. Okay, this is exactly equal that equation y equal to mx plus c. Okay, so then our model becomes y equal to beta naught plus beta 1x plus epsilon, where epsilon is some error term. So if you see here, whenever we are plotting this regression line, we are not exactly passing through each and every point. We are passing through, in between these points, such that the vertical distances between these points are reduced. Okay, this is the concept of fitting a linear regression, simple linear regression. Alright, so here we call beta naught as the intercept and beta 1 is our slope and epsilon is that random error. Alright, now in order to fit this model, we need to find out some estimates of beta naught and beta 1, because these beta naught and beta 1 are actually unknown parameters which is not known to us. Had this been exactly known to us, we would not have required this error term. Okay, if something is very deterministic that this is going to happen, then beta naught and beta 1 are probably known and we don't need this epsilon. But in data analysis and real life situations, we are trying to find the linear relationship between variables x and y based on a small sample, let's say. Okay, so there will be some inherent error which is already involved. Now how do we estimate beta naught and beta 1? We are coming to that. Now before proceeding to the estimation, there are certain assumptions. Okay, so here this is the model. I can write it as yi equal to beta naught plus beta 1 xi plus epsilon I, where I stands for ith individual. Okay, and I can range from 1 to n. So if this is my model, I can have n individuals. So this essentially means is what it means is that I have n individuals or n entities rather with x1 y1 to xn yn. Alright, now if I have this model in mind, there are certain general forms and assumptions. The first assumption is that epsilon I is a random variable. Expectation of epsilon I equal to 0 for all I. Variance of epsilon I equal to sigma square for all I. And covariance between epsilon I and epsilon j is equal to 0 if I not equal to j. So what it essentially means is that the expected error is actually 0. Variance of the error terms remains the same across all individuals. This assumption is called the assumption of homoscedasticity. And also we have this, that the error terms are independent of each other. The error term for ith individual will not be correlated with the error terms of jth individual. Okay, Here we are measuring covariance strictly. The other assumption is that these x's are not random. Okay, so x is not random, or we could also say non-stochastic. Okay, so epsilons will be a random variable with expectation epsilon 0, variance epsilon sigma square for all I, and covariance between epsilon I and epsilon j should be 0 if I not equal to j, and x's are not normal. There is one more assumption which doesn't come with the Gauss-Markov theorem, but we use it specifically for testing of our hypothesis. Okay, so this is not inbuilt in the Gauss-Markov theorem, but still we are going to say that the epsilons follow a normal distribution. Okay, with combined with the previous assumptions, we have epsilon I follows normal 0 and sigma square for all I. Okay, and since they follow a normal, since this is also an assumption for testing, since they follow normal 0 1, due to this normality, we can say that covariance of epsilon I epsilon j equal to 0 if I not equal to 0, it implies that the errors are not only uncorrelated but also independent. Okay, so these are some general assumptions that we have, that we need to make before we not this one, we don't need this assumption, this is not needed for estimation, but is required for testing of our hypothesis. All right. Okay, so now that we have certain assumptions in place, how do we estimate the betas, and what is the logic and how do we derive it? So remember, I was talking about some scatter plot. So this is your x and this is your y, and here is the scatter plot that I was talking about. Our goal is to fit a line such that these vertical distances are reduced. Okay, now what exactly is this vertical distance? Let's say this is my y, this point actually is my y observed. Okay, and if I project this line vertically onto my regression line, then the point on the line, let's say this point, is actually my y predicted. Okay, so observed minus predicted is what is it quantifying? It is quantifying error. Okay, so this y observed minus y predicted is actually my error, and the goal is to minimize error as much as possible. All right, now in order to minimize error, we can have three possibilities. We can say that we are minimizing the, what do I say, since this is predicted, errors will be so the errors are I mean, whenever I have y predicted, I am going to say error as residuals. Okay, so if errors are designated by epsilon, residuals are designated by e. So I can say that summation ai, if it goes to 0, this is one case that I could have. I could say summation of mod ai goes to 0, something like this, or not 0, I would rather say minimize either this quantity or this quantity or summation ei square. So 3 types of minimizing I can do. The problem in minimizing this one is that some ei's will be positive. So some ei will be positive and some will be negative. So summation ei may become 0 as well, but I would still have errors. For example, if these points are equidistant from the center, all the points, if they are equidistant from the center, then we could have a perfect summation ei equal to 0. But that does not guarantee that there is no error margin involved. Okay. So what we are focusing is that we are going to minimize. So this option is not valid. So amongst the other two, what is usually done is that this is the preferred quantity which we are going to minimize, which is the sum of squares of residuals. Okay. So how do we exactly do it? We minimize so how do we do this? We minimize summation we minimize summation yi minus yi hat whole square. Okay. Now yi is observed, and whenever I give this hat sign, it means it is predicted. Okay. So yi hat is actually beta naught hat some estimate plus beta 1 hat xi, because this is the fitted regression line. Okay. So this is my sum of squared of residuals, and I am going to minimize that. Alright. How am I going to minimize? First I'll put these terms here. So we have yi minus beta naught hat minus beta 1 hat xi square. So this is the quantity that we want to minimize. So applying maximum minima, what we are going to do is that we are going to differentiate this with respect to the parameters and equate it to 0. So del s del beta 1 hat and del s del beta naught hat will be equated to 0. Okay. So this will be my equation 1 and this will be my equation 2. So from these two equations I am going to have two normal equations. Okay, these actually will give me my normal equations. So I am going to do it just quickly for all of you. So if I do del s del beta naught, what I have is that summation, this 2 will come here, 2 yi minus beta naught hat minus beta 1 hat xi equal to 0 into minus 1, because coefficient of beta naught hat is minus 1. And also I am going to have here 2 yi minus beta naught hat minus beta 1 hat xi into minus xi. This is also equals to 0. Okay. So if we take this to the other side, what we have is essentially summation of ei equal to 0 and summation of ei xi equal to 0. So these two are my normal equations. Now solving, so from these two we have two equations containing beta naught and beta 1. So solving these two, we can solve these two equations simultaneously, and we'll get the value of beta 1 hat as something like this. This would be summation xi minus x bar yi minus y bar by summation xi minus x bar square, where x bar is 1 by n summation xi and y bar is 1 by n summation yi. Okay, and substituting this in the other equation, we are going to get beta naught hat as y bar minus beta 1 hat x bar. Okay, so solving these two equations simultaneously, we are going to land up at this solution. Okay, so this is how we estimate beta. So this beta naught and beta 1 is estimated in such a way that this vertical distances between the predicted y and the observed y is minimized. Okay, and then finally I am going to tell you a little bit about interpretation of regression coefficients. So now we have beta naught hat and beta 1 hat. So in case of a simple linear regression where we have y equal to x, if we have something like this, then this is your beta naught and the slope is your beta 1. Alright, so then what does this mean? Beta naught means that, so what we have this predicted equation beta naught plus beta 1x. Okay, so if beta naught hat is non-zero, it means that even if x is 0, y is predicted to have some value. Okay, and what do we mean by beta 1 hat? Beta 1 hat means how 1 unit increase in x is affecting y, because it is exactly the slope. So it will give you delta y by delta x. Okay, so if let's say I have, going back to the crop example, if I have something like this y hat equal to beta naught hat plus something beta 1 hat into x, where x is the rainfall in cc, let's say. So what beta 1 hat is giving me is that how much increase in the yield or decrease in the yield can be observed if there is 1 cc increase in rainfall. Usually it is for this crop example, if beta 1 is positive, it means that increase in rainfall is going to increase my yield. Similarly, for that revenue example, if I have something like this and beta 1 hat is positive, then we can say that increasing my spend on ads by 1 rupee or whatever metric that we are considering by 1 rupee is going to increase my revenue by how many rupees. Okay, so this is how we should interpret linear regression coefficients, simple linear regression coefficients. Okay, so be mindful, this interpretation is for regression coefficients of a simple linear regression. For a multiple linear regression, it's not that straightforward. But for a simple linear regression, it means how much one unit increase or decrease in x is increasing or decreasing y. Alright. And then we come to testing of hypothesis. Now we have a set of x and y. We have xy coordinates for 1 to n individuals. We plot a scatter plot and then we fit a linear regression line, and then we have something like this. So then if now somebody gives me an x, I am going to tell or I am going to predict a value of y. The next thing that I am worried about is that whether these are significant in predicting y or not. So what I mean to say is that these may be very large quantities, these may be very small quantities. X will only have an impact on y if beta 1 is not equal to 0. Okay, but if beta 1, the original parameter, if beta 1 is equal to 0, then x may have some value over here, but actually it doesn't impact y. Then incorporation of this x into the equation can lead to misinterpretation. For example, if something is very, very trivial and maybe just because of chance or something else, we have some small 0.0002 value over here. Now we want to see if this value is significantly different from 0, and that is where we conduct test of hypothesis. Okay, so we could test 3 hypotheses, to be very honest. One is that whether the beta 1, the slope, is actually equal to 0 or not. The second one is whether the intercept is equal to 0 or not. And the third one is whether the regression holds or not, that is beta not equal to beta 1 equal to 0. So if you have followed the lectures, you would have seen that this is actually conducted by a t-test. This is done, sorry. So these two are conducted by a t-test, and this one is conducted by an f-test. Okay, so we'll talk about it a little more and then we'll go on to the problem solving. So how do we proceed with the test of hypothesis? Now, if we had assumed in this model that epsilon I, expectation epsilon is 0, variance of epsilon is sigma square, and we had additionally assumed y follows normal, sorry, not y, epsilon follows normal 0 sigma square. Okay, so from beta 1 hat, what do we have? Beta 1 hat is this thing. This also follows, if these assumptions hold, then this follows a normal beta 1 and sigma square by sxx, where what is sxx? This is summation xi minus x bar whole square. Is it all right? And we have also seen beta naught, this also follows normal beta naught sigma square, but not only sigma square, this is 1 by n plus x bar square by sxx. Okay, so from here what we can see is that beta 1 and beta 1 hat and beta naught hat are unbiased estimators of beta 1 and beta naught. Why do I say unbiased? Unbiased because expectation of beta 1 hat is beta 1 and expectation of beta naught hat is actually beta naught. Okay, so if expectation of theta hat equals to theta, then we say that this hat term is an unbiased estimator of the actual parameter. Okay, now with this context, let us move on to some questions. Okay, and when we solve those questions, we will be able to know more about how to conduct this test of hypothesis actually, and then find out how to get the critical points and do this sort of an analysis. Okay, so far is there any doubt, ma'am?
I don't have any doubt.
Okay, ma'am, fine. Sorry, I didn't. Were you saying something, ma'am? Okay. So if not, I'll just proceed to the problems. So let's say here we have a question that the moisture of the wet mix of a product is considered to have an effect on the finished product density. Okay, and the moisture of mix was controlled and finished product densities were measured as shown in the following data. So here what do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 data points. So here our n is actually 12. And this is given to us summation x, summation y, summation x square, summation y square and summation xy. Now we are fitting this simple linear regression to this data. Then what will be the least square estimate of beta 1? So least square estimate of beta 1 hat, beta 1 is designated as beta 1 hat. This should be summation xi minus x bar, yi minus y bar by summation xi minus x bar whole square. In the lecture it is written as sxy by sxx. Okay. Now if we simplify this further, we are going to have it as summation xi yi minus n x bar y bar by summation xi square minus n x bar square. Okay. If we multiply xi and yi, we will have xi yi minus we will have summation xi into y bar. So summation xi is nx bar. Then again we have minus x bar into summation yi, that is minus x bar ny bar. So what we have till now is minus 2x bar y bar and then again plus of 2n x bar y bar and then minus minus will be plus, x bar y bar will come out and summation over I would lead to n. So minus 2n x bar y bar plus x bar y bar is minus x bar y bar. Similarly, this will also happen here, and we are down with this thing. So we plug in the values. What do we get? This will be 339.1 minus x bar is 63.6 by 12. So 63.6 by 12 will be 5.3. Okay. So here we have, this is 339.1 minus x bar is 5.3 into, and ny bar is actually 62, it's given. So we have 62 by, this is summation xi square, that is 339.18 minus nx bar square. So that would be n mean 12 into 5.3 into 5.3. So if we solve this, then what do we land up on? This is 339.1 minus 5.3 into 62. So denominator is 10.5 by 339.18 minus 12 into 5.3 into 5.3. So this will be 2.1. So this is actually 5. So therefore the least square estimate of beta 1 is 5, and this is my answer. Alright, now if we want to know the least square estimate of beta naught, as in this question, then what are we going to do? We know that from previous question, beta 1 hat is 5, then beta naught hat would be y bar minus beta 1 hat x bar. So that would be 62 by 12 minus beta 1 hat is 5 into x bar. X bar is how much? 5.3. So this is how much? This is 5.16. Okay, so minus 5 into 5.3, so we can write it as 5.17167 5.167 minus 5 into 5.3. So we'll see how much it amounts to. 5.167 minus 5 into 5.3. So this is actually minus 21.333. Okay. So if we have to interpret this thing, it is that even if the moisture of the wet mix, even if it is 0, the finished product density would be something close to minus 21.333, and as the moisture of the wet mix increases by 1 unit, this density is also going to increase by 5 units. Okay, fine. Now we come to this thing, degrees of freedom of SS residuals. SS residuals is nothing but sum of squares due to residuals. So this we can write as summation, so S is residual, we can write as summation ei square. Okay, that is summation yi minus yi hat whole square. Alright. Now, if you solve this, this one can be written as syy minus beta 1 hat square into sxx. Okay, the derivation is given in the lecture notes. So this is nothing but syy is summation yi minus y bar whole square, and this is minus beta 1 hat square. Sxx is summation xi minus x bar whole square. So this again means summation yi square minus n y bar square minus beta 1 hat square into summation xi square minus n x bar whole square. Now this part we have already calculated. Okay, this part is how much? This part we just calculated here. Sxx is 2.1. So this one we have. Then what do we need? Summation yi square minus n y bar square minus beta 1 hat square into 2.1. So this here we have as 390 minus n y bar square. So this means n y bar means 62 into 62 by 12 minus 25 into 2.1. So we will just calculate this. So this comes to 17.166. So we'll write it as 17.17. That is our answer. So sum of squares residuals is actually 17.17. Okay. Now moving on. Here we have been asked what is the degrees of freedom of sum of squares due to regression. Okay, the previous question was not to find out the sum of squares due to residuals, it was to find out the degrees of freedom. Okay, now about the degrees of freedom, we should know this thing. So the total variance, okay, this is actually partitioned into two components. So y equal to beta naught plus beta 1 x is your regression part and epsilon is your error part. Now this total sum of squares, that is syy, is giving me the variance of y. Why? Because variance of y we can write it as summation yi minus y bar whole square 1 by n. Okay. So 1 by n will cancel out from each of the sides. So we are just considering the numerator in this case. Now in case of a linear regression, what happens is that this total variation in y is partitioned orthogonally into two components. One is the SS due to regression and the other is SS due to residuals. So this captures the variation that is captured, that can be addressed by the regression line, and this sum of squares due to residuals is actually capturing the variation due to the presence of errors. Okay, so this total variance in the response is orthogonally distributed between SS regression and SS residuals, and the degrees of freedom of these terms are also similarly linearly related. Okay, so if you add up the degrees of freedom of sum of squares due to residuals and the degrees of freedom for the sum of squares due to regression, you are going to get the degrees of freedom of SST. Now, what is the df of each of these components? SST df is actually n minus 1. Now, why so? Because SST means what? Summation yi minus y bar. Okay. Now, if I equal to 1 to n, now if I have n data points and this is the SST figure, then if I know y1 to yn minus 1, I will be, and I already know y bar, so there is one constraint, that is summation yi equal to y bar. So due to the presence of this constraint, we have n minus 1 degrees of freedom. What I mean to say is that the moment we know y bar, only knowing n minus y is going to serve my, is going to serve my purpose. I don't need to know all n y's in order to find out this quantity, because I have this constraint, summation yi equal to y bar. So because of this reason, I only need any of the n minus 1 y's. I can choose them freely. That is what is meant by degrees of freedom, that I can choose n minus 1 y's freely, because the moment I choose n minus 1 y, I will know what the nth y will be because of this linear constraint that we have. So SST df is actually n minus 1, and SS residual df is actually n minus p, where what is p? P is the number of unknown parameters. Okay, not variables, mind you, but parameters. Okay, so let's say I have, here we have what? Y equal to beta naught plus beta 1x plus epsilon. So here in this case my p is actually 2, because I have two unknown parameters. I have one variable. Okay, this is my one predictor variable, but I am going to consider unknown parameters which are estimated. So this, in this simple linear regression, this is one parameter and this is one parameter. So here we have p equal to 2. Therefore, in this scenario, we have SS residual as n minus 2, and therefore here how many n's do we have? In the question it is given, here we have n equal to 12, and so the degrees of freedom of SS residuals is actually 10, which is n minus 2. Okay, just to give you a brief update, this partitioning, this holds true even for a multiple linear regression. So what I am trying to say is that this SST equal to SS regression plus SS residuals, This will hold true even if we have something like beta naught plus beta 1x plus beta 1x1 plus beta 2x2 plus epsilon. So in that case, SSTDF remains same, it will be n minus 1. And this one SS residual DF will be how much? This will be n minus number of parameters. So here in this case we have 2 predictors but 3 parameters. So here we will have n minus 3 and SS regression will be 2. Okay. So for this case we have SS residuals as 10, which is n minus 2. Similarly, the degrees of freedom for SS regression. So as I was telling, SST equal to SS regression plus SS residuals. Now this is n minus 1 and SS residuals is n minus 2. Therefore, SS regression will be 1. Okay, and that's the answer. Moving on. Yeah. So now we have calculated betas, we have calculated SS regression. Now we want to find out the value of MS regression, MS residuals, sorry. So MS regression means SS regression by DF of SS regression. Similarly, MS residuals means SS residuals by DF of SS residuals. So SS residuals we calculated here. SS residuals, the value was something 17.17. So this is actually 17.17 by DF SS residuals is n minus 2, that is 10. So this one MS residual is actually then 1.717, and that's the answer. Is it okay? Okay. Now we move on to testing of hypothesis. So as I was saying, we have found out beta naught hat, beta 1 hat, everything. And then now we want to test whether beta 1 is significantly different from 0 against beta 1 not equal to 0 with alpha. This is actually my level of significance. Okay, and we want to know what the decision should be. Alright, so for this thing we should have a test statistic in mind. So here what test we are doing? We are testing for slope coefficient. Okay. Now we know that beta 1 hat follows normal beta 1 and sigma square by SXX. Okay, therefore if we transform it to a z statistic, we can write it as beta 1 hat minus beta 1 by root over sigma by SXX. This should follow a normal 0 1. We are just standardizing, subtracting the expectation and dividing by the standard deviation. Okay, so this transformation will give us beta 1 hat minus beta 1 by root over sigma by SXX will follow a normal 0 1. Okay. and here nothing is mentioned about sigma square. So when nothing is mentioned, we would assume, one second, so so when nothing is assumed, we are going to assume that sigma square is unknown. Another thing is, what happens if sigma square is known? We'll come to that. So first let us consider the case where sigma square is known. So if sigma square is known, we have this thing, beta 1 hat minus beta 1 by root over sigma square by sxx. This follows a normal 0, 1. Now under h naught, beta 1 hat, beta would be 0 if h naught is true, by root over sigma square by sxx should follow a normal 0, 1. So if this is the scenario, then this can be my test statistic. What, by definition, what do we mean by a test statistic? A test statistic is a function of the observations only, okay, and it doesn't contain any unknown parameters, only based on observed variables, okay. So then this quantity beta 1 hat is also based on y and x, sigma square if it is known, and sxx is also based on x's. Then this thing becomes a test statistic under h naught. So when h naught is, I'll come to sigma square unknown case later. So when sigma square is known, we can say that this follows a normal 0, 1. So now we know how a normal 0, 1 looks like, okay. So this is a bell shaped curve, okay. This is 0 and then it is distributed about 0. Now if beta under h naught, if h naught is true, then beta 1 hat, this is the test statistic and this is the distribution. Ideally it should follow, it should be centered around 0 and should have a variance of 1. So if that is the case, now if t observed is way more than 0, like beta 1, because t observed, what does it have in the numerator? It has beta 1 hat. So beta 1 hat, if it differs way too much from beta, so let's say beta under h naught, this is the 0. So if beta 1 is too positive or beta 1 is too negative, then this test statistic is going to fall somewhere near the tails. It could fall here, it could reside on here, somewhere here, or it could also reside somewhere here. Now if this is the case, the test statistics falls in one of the end regions or the tail regions of our distribution, then the natural thing is that, okay, then beta 1 is significantly different from 0, and then we should say that, okay, then the predictor has an effect, positive or negative, depending on the sign of beta 1 on our response, okay. So we set the rejection rule So this is the intuition behind this rejection rule, that if T observed, or rather modulus of T observed, is greater than, let's say, some critical value, then we reject H naught beta 1 equal to 0 and conclude that X is significant. Okay. Now, how do we choose this critical value? This critical value is chosen based on our level of significance, that is alpha. Okay. So, here we have been told that alpha should be 0.05. So, we are choosing this distribution in such a way, we are choosing the cutoffs in such a way, I should say. So, we are choosing these blue cutoffs in such a way that this area below this cutoff and this area above this cutoff, they add up to, so this total, let's say A1 plus A2, A1 plus A2 should be 0.05. Now, since this is symmetric, these points are chosen such that A1 is equal to 0.025 and A2 is also equal to 0.025. Okay. For a normal distribution, these points are 1.96 and minus 1.96. Okay. I'll also tell you how to find out these numbers from tables and softwares, but for the time being, just listen to this. So, for in case of a standard normal distribution, if the area below minus 1.96 is 0.025 and the area above 1.96 is 0.025. So, these two areas add up to 0.05. Now, since we have a both tailed test, that beta equal to 0 against beta 1 not equal to 0, this is our rejection rule. So, if we modify our rejection rule a little bit more, then we can say that we reject H naught if and only if modulus of T observed is greater than 1.96. Alright. So, if this holds true, then it means what? That beta 1 is way far from actual 0. That means what? That this x variable, which one unit increase of that which increases y by beta 1, is significantly affecting the response variable. Alright. But all of these holds when the normal distribution holds as is, like 1.96 and 1.96. This will only hold if sigma square is known. If somebody already tells you that variance of epsilon I is given as 5 or some sigma square which is known. But most often than not, this is not the case. Mostly what will happen is sigma square will be unknown. So, what do we do in those cases? Sigma square unknown. Then the problem is this thing T equal to, or rather capital T equal to beta 1 hat by root over sigma square by Sxx. This is no longer a statistic. Why? Because sigma square is another parameter and a statistic cannot have any parameter in it. Is it okay? So, then what do we do? How do we tackle this situation? Now, we have also seen something like this. So if this thing n minus 2 ms residuals by sigma square also follows chi square n minus 2. And we have also seen beta 1 hat follows normal beta 1 sigma square by sxx, and these two are independent. This can be shown. Alright. So if this holds true, then under H naught, what is happening is beta 1 hat is following normal 0 sigma square by sxx, and n minus 2 ms residual by sigma square, this also follows chi square n minus 2 independently. Okay, chi square is another positively skewed distribution, and normal is the normal standard bell curve. So there is another distribution which is known as the T distribution. It is also symmetric about 0. Okay, and a T distribution is it is devised in this way. It is actually a ratio of a standard normal by root mean of chi square. Okay, and this normal 0 1 and the chi square distribution should be independent of each other. This is how a T distribution is designed. So in our case, what do we have? Here we have beta 1 hat by sigma by root over sxx. This follows normal 0 1, and n minus 2 ms residuals by sigma square. This follows chi square n minus 2. So therefore, this thing normal 0 1 by mean root mean chi square is how will we designate this? So we can write as beta 1 hat by sigma by root over xxx whole divided by root over root. Now mean expectation of chi square n minus 2 is n minus 2. Whatever the df is for a central chi square, this will be the expectation will be that. So mean chi square is root mean chi square is what? This is n minus 2 ms residual by sigma square divided by n minus 2 because of this thing. So this is going to follow a T statistic. Now here what do we have? Here we have beta 1 hat by sigma by root sxx by, here we have root over ms residual n minus 2 by sigma square into n minus 2. This n minus 2 cancels, and this sigma and this root over sigma square, this also will cancel. This follows a T distribution, and then finally we have beta 1 hat by root over ms residuals by sxx. So when sigma square was known, we had sigma square by sxx, which follows a normal 0 1, but here when sigma is unknown, we are estimating sigma square with ms residual, and then this is the test statistic. Every quantity is known, beta 1 hat is known, ms residual we can calculate from SYY beta 1 hat and sxx is already known. So this is purely based on observations with no parameters. This under H naught, because beta 1 is 0, we have not put it here, under H naught, this follows a T distribution with n minus 2 degrees of freedom. Okay. Now the logic remains exactly the same. If beta 1 is significantly different from 0, then T value should also be further and further away from 0. It can be on both the sides, right? So as I was saying, T distribution is also this normally distributed, not normally, this is a T distribution which is also symmetric. Okay. This is also a symmetric sort of a distribution. So if beta 1 is significantly larger or lesser than beta 1 equal to 0, if it is way different from 0, then for here also my T, the T observed T that I am going to have, is either going to fall in this extreme or it is going to fall in this extreme. So similarly, I am going to set cutoffs over here. So this will be my lower tail and this will be my upper tail. And since this is a symmetric distribution, I am going to designate this area. The area will be 0.025 below this, and the area above this will be also be 0.025. Now what I need to do is that I need to find out cutoffs from a table or a software such that my rejection rule is satisfied. So we will reject H naught if and only if modulus of T observed is greater than T n minus 2. This one we will call as alpha by 2. The naming is in such a way that T n minus 2 alpha is the upper alpha point, which means that area above this point is area above this point is alpha. So here alpha is 0.05 and we are distributing alpha in two regions. So this, if modulus of T observed greater than T n minus 2 alpha by 2, then we are taking both the situations. What it means is that either T observed is greater than T n minus 2 alpha by 2 or T observed is less than minus T n minus. So this point is minus T n minus 2 alpha by 2. Okay. And this is, because this is symmetric, this is T n minus 2 alpha by 2. So following this similar logic, if my T observed value is in the extremes, then we can say that beta 1 is significantly deviated from 0, and so we can say that beta 1s are significant, which implies that the predictor X is significantly affecting my response. Okay. Now the question is, how do I find out these cutoff points? So these can be found out from tables like this. Okay. So here what this means is that this is two tails. So what do we need? We need this point. Alright. T.975. It means what? That point in the T distribution such that the area, this cumulative probability means left hand side. So left hand side is 0.0975. So right hand side will be 0.025. Okay. So this is the column that currently we are interested in. And what is the degrees of freedom that we have? Here we have n minus 2. So we are going to find out this one, 10. So what is that point? Cutoff point is 2.228. Alright. So then the rejection rule is that we'll reject H0 if and only if mod of T observed is greater than 2.228. Okay. So now let us just calculate from here what do we have as our beta 1. So here in this example, it has not been said whether sigma square is known or unknown. So what are we going to do? We are going to consider that sigma square is unknown, and then we are going to finally perform this test. So what can we do? We are going to write down the test statistic that we just wrote and then see if it exceeds that 2.228 value that we finalized on. Okay. So here, what is the test statistic? So the test statistic is beta 1 hat by root over ms residual by sxx. Okay. So this will be my T observed. So beta 1 was what? 5 by ms residuals was what? We found out 1.17, 1.717 by sxx was 2.1. So root over this thing. So we'll find out what the value is. This is 5 divided by 1.717 divided by 2.1, and then we also have a square root. So this is what? This is actually 5.52. So this is T observed is 5.52, and from that table we understood that if this is the T distribution, this point is 2.28. So this point is minus 2.28, and below this area is 0.025. Above this area is also 0.025. So our test statistic, if this is 0, then our T is lying somewhere here, 5 point something. So this is lying in the critical region. It is way more than this value. Therefore, our decision is we will reject H0, that beta 1 equal to 0. We are rejecting H0. Why? Because beta 1 is significantly further from 0. So, and thus we conclude that beta 1 is significant, or in other words, what the question demanded? Moisture of the wet mix is a significant predictor of density, product density. Okay, this is the interpretation. All right. Now similarly, if we are to test for the hypothesis this one, H0 equal to beta naught minus 15 against H1 beta naught equal to minus 15 with alpha 0.05. Again we have the same logic. Here also we have unknown. Okay, what would have happened if it was a known situation? Cases where sigma square is known, then we know beta naught hat, it follows normal beta naught, sigma square 1 by n plus x bar square by sxx. Sigma square is known. So T would have been beta naught hat minus beta naught by sigma square 1 by n plus x bar square by sxx root over this thing, and then under h naught we would only have this term, and then it would have also followed a normal 0 1, and then since the alternate hypothesis is beta naught not equal to 0, we also would have this normal curve 0 and then minus 1.96 and 1.96 based on this area. Above should be 0.025 and below also should be 0.025, and we could have gone and carried out this analysis, and the rule would have been reject H naught if and only if T observed mod T observed is greater than 1.96, okay, which means it either falls in this region somewhere here or it falls somewhere here, okay. But this was the case when sigma square was known. What do we do if sigma square is unknown? Here also we are going to follow the same procedure as before, okay. If sigma square is unknown, then there is nothing to worry. We have this thing beta naught hat follows normal beta naught sigma square 1 by n plus x bar square by sxx, and we also have this thing, so that is n minus 2 ms residual by sigma square. This also follows chi square n minus 2 and they follow independently. Alright, so then beta naught hat by this thing sigma square 1 by n plus x bar square by sxx by again root mean chi square root over n minus 2 ms residual by sigma square by n minus 2, that is the df of the chi square distribution. This should also follow a t distribution with n minus 2 degrees of freedom. Alright, so then sorry, this one there will always be a root over here. So then the test statistic is what? The test statistic is beta naught hat by root over ms residual into 1 by n plus x bar square by sxx okay. So this is my T observed, and the rejection rule will be reject H naught if and only if. So from this, since the degrees of freedom is not changing, this is our cutoff point if modulus of T observed is greater than 2.228. Now we will find out this thing. Beta naught hat was how much? Minus 21.33. ms residual was 1.717. 1 by 12 plus x bar square was how much? 5.3 square by sxx was how much? 2.1. So let us just calculate this thing. So this will be minus 21.33 this one divided by square root of 1.717 into 1 by 12 plus 5.3 square divided by 2.1, close bracket, close bracket, close bracket, close bracket. Yeah, so this is coming to be something around how much is it coming to? Okay, so this is not this thing. One second. Here we are not testing beta not equal to 0. Here we are testing beta not equal to minus 15. So here we would have the test statistic as minus 15, and here also we would have it like minus 15. So then this would mean beta naught hat minus 15. So this would be minus 38.33. So if we do this minus 15, no, 36.33, sorry, 36.33. We'll just find out how much it amounts to. 21.33, 21.33 plus 15, 36.33 divided by square root of 1.717. Okay, let me just calculate this thing. 5.3 square is divided by 2.1. This amounts to 13.376 plus 1 divided by 12. This is 13.459 into 1.717. This is 23. The square root of this thing is 4.807. So this is actually minus 36.33 by 4.807. So this is minus 36.33 divided by 4.807. This is also something around 7.55. So since T observed is greater than 2.228, therefore the decision is also, here also the decision is to reject H naught and conclude that beta naught is significant, which means to say that even if we don't have any wet moisture, the density is going to be affected. All right. So this is how we conduct a test of hypothesis. And now one more thing is this thing, moisture of the what does this ratio MS regression by MS residual yield? Okay, so this one is actually ratio of two chi-square variables. All right, so therefore MS regression by MS residual is going to give me an F statistic. Is it okay? All right. So now that we know how to manually do it, I'm also going to show you how you can do the same thing in a software. Okay, you can also use Excel to do your calculations, but these things can also be easily done with the R software, which is very helpful in doing these statistical operations. So very quickly I'm going to show you, I'm going to demonstrate how you can find out all of these and generate the ANOVA table that we had generated earlier, sir had demonstrated in class how to generate the ANOVA table. So how we can do that using this software. So quick demonstration. Before that, I'm going to stop the screen. I'm going to present the R web window. Okay, I hope you can see my R console. So this is actually a software called R. It is open source, freely available. You can just go ahead and download. You can either download R Studio or you can download plain and simple R, and then it gives you an interface, a better interface to look at the files and all those kind of things. So right now the question is, I want to fit that linear regression using this software. So how am I going to do that? So first is I'm going to assign two vectors, and that would be the vector of x and the vector y. Okay, so C is used to sort of create the vector. It will be created using a comma separated list. So you can know more about R and its data structure from online resources, but I'm just going to show you the regression part and also urge you to verify your findings using this software when you practice. All right, so that you know that there's no calculation mistake. But during your exams, the software won't be available to you. Maybe a digital calculator, not a digital calculator, some inbuilt calculator may be made available to you, or you will be provided with the values. So in any case, you need to know the formulas and how to solve the equations, but this is for your learning that I'm demonstrating this. Okay, so here x is moisture, and it has these values: 5.7, 4.7, 5.0, 5.2, 5.2. Okay, then 5.9, then we have 5.2, then we have 5.3, then we have 5.9, then we have 5.6, and we also have 5.0. all right. Similarly, for y, we are going to put the values: y equal to 3, 3, then we have 4, 5, then we have 10, 2, then we have how much, 9, 3, then 7, 6, 6, 4. Okay, so in order to run it on R Studio, I am going to do Control Enter. Okay, so here I see this is a numeric vector. There are 10 values over here. Should have been 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But I have input 10 values. So maybe I've missed some. 4.7, 5.0, 5.2, 5.2, then I have 5.9, then I have 4.7, which I missed, then I have 5.9 again, then I have 5.2, 5.3, 5.9, 5.6 and 5. Similarly, y is 3, 3. So if I enter this thing, y is also a vector with 12. Here we can see n equal to 12. Now in order to fit a linear regression, the command is lm y on x. That's it. So see, if we do lm y on x and press command enter, we have intercept estimate as minus 21.33 and your slope estimate is given with the variable name. So here my predictor variable name is x, so the slope coefficient is 5. Alright, now if I store this, if I write it as my model, and if I give summary model, let me see what I get. So summary model is going to give me this thing. Alright, so from here you see this is the minimum first interquartile, third quartile of the residuals, and here in this coefficient term I am going to get the estimates, the standard errors. What are the standard errors? Standard errors are nothing but whenever we were calculating the test statistic, if you remember, in the denominator square root of sigma square by sxx in case of beta 1, sigma squares we were replacing by ms residual. So that denominator quantity root over that thing is actually the standard error. Okay, and then this by this is going to give you the t value. Okay, you can go back and check, we also had something like this 5.53, and for this intercept the t value is differing, so maybe we have made some calculation mistake. And to check whether we have landed on the correct decision or not, this r is going to give us something like this. Okay, so this is not actually the exact cutoff value that we were considering or the level of significance of 0.05. This is actually something called p value. I'm going to tell you what it means by a p value. So if from this R software, if you see that the p value reported in this column is less than your level of significance alpha, then we can say that it is significant. For example, here you see these are codes. So here we have 2 stars, which means that this is actually less than even 0.01, or sorry, this is 0. Okay, so yes, this is less than 0.01. So here if you see something like star, 1 star, 2 star or 3 star, then you can safely say that this is less than the 0.05 level of significance alpha that was mentioned in the paper. Now here our decisions are the same. We also said that intercept is significant. Here we can see 2 stars, it's less than 0.05, and here also we can see this p value is less than 0.05, so beta 1 is also significant. Alright, and this p value here 0.000251 is actually the p value of the third hypothesis that we were talking about. Okay, so if you remember, we were talking about a third kind of hypothesis which was here. Where is it? So this test, if you remember, that's beta naught equal to beta 1 equal to 0. This test's p value is the one which is reported at the end, the last p value that we were saying. Okay, and now I'm going to tell you what exactly we mean by a p value, so that it becomes easier to demonstrate. So here let's say this was our normal distribution or t distribution whatsoever, and we designated cutoff points over here, in here and here, and then we said that if this point falls here or if this point falls here, then we are going to say that our decision is reject the null. Similarly, this is equivalent to saying that if I would have had a distribution like this, and let's say this is the cutoff, and my test statistic falls here, okay, or t observed it falls here, then if I would have drawn a line from here, okay, then the area below this line and the area above my test point, observed point, if I add these two up, this is going to give me my p-value, okay. And so if this total area beyond the green line, if it is less, so if p-value, sorry, so if this area sum is giving me the p-value, then if we can say, so this area plus this area is giving me p-value, but it's not crossing that cutoff area. So blue plus blue, this entire area, this was supposed to be 0.05. So then if I can say that p-value is this green area, so if p-value is less than 0.05, then also we are rejecting H0, because that means that this point falls beyond the cutoff positions, okay. So p-value for a two-sided test, as we were discussing, is probability that this distribution is greater than t observed, which means that the area above t observed and area below t observed, okay. Now these tests will be accordingly modified based on whether we have a one-sided hypothesis or not. If we had a one-sided hypothesis for all of these tests, then if H1, let's say, would have been beta 1 greater than 0, then our rejection, this would have been our rejection rule. Beta 1 greater than 0, then we would have only considered a right tail test. We would have considered that point such that the area above which is 0.05, and then the p-value would have been probability t greater than t observed, okay. If we would have had a left tail test, beta 1 less than 0, then also same thing, we would have considered this end and this as our cutoff, such that the area below should be 0.05 and the p-value would have been calculated as probability t less than t observed, okay. And also one more thing I just want to show you, we found out how to get the cutoffs from the table, but how do we get the cutoffs using the software? That also I'm going to show you. So for that, okay, so for that we need to know some commands, okay. For norm, if we want to find out probability x less than 5 something, okay, where x follows normal 0 1, okay, then what do? We use p norm and we give 5, mean equal to 0, SD equal to 1, those kind of things, t equal to 1 and lower dot tail equal to true. and then we get this probability, that probability x is less than 5 for a normal 0 1 distribution. But if we want to find out the quantiles, what we need is q norm, okay, and we want to find out that value above or below which this area lies. So what we wanted is, let's say I want that value in the normal distribution above which 0.025 area lies. So what I'm going to do is that 0.025, okay, q norm, mean equal to 0, this is the default value, you can also change, and I want that point such that this area 0.025 is the area above the cutoff. So I am going to give lower dot tail equal to false. So you see I am getting this 1.96. Okay. Similarly, for t distribution I am going to give qt 0.025, df I have to give. So df was n minus 2, so 10 in my case. I did not have any non-central criteria, and then I would give lower dot tail equal to false. So here you see, here also I am getting 2.228. Okay. So for any distribution you can just navigate through these options and commands: p norm, q norm, pt, qt, pf, qf, p chi square, q chi square. Okay, and if you face any issues, just go to this command and press F1, and then you are going to find out this documentation window will open, and you will be able to read and find out what each of these mean and how you can navigate through it. So this was all. Sorry, I had lost connection. So this is how you can conduct a simple linear regression and then carry out a test of hypothesis for the significance of the estimates. Okay, so today I'm going to stop here, and then I'm going to see you in the next class. Meanwhile, if you have questions, please post in the discussion forum. Thank you so much.